Hello, and welcome back to Hypnosphere. You have found a quiet corner of the universe where we can rest, breathe, and learn at a gentle pace. Here, curiosity does not rush. It opens like a night-blooming flower, slowly, in calm air. Tonight we are going to step into an idea that has fascinated storytellers and scientists alike. An idea that feels both impossible and strangely close. We will explore the strange possibility of time travel, not in the frantic glow of movie plots, but as a soft, careful science narrative. We will walk through ideas you may have heard, and ideas you may not have, then settle into what physics really allows us to do. If you feel comfortable sharing, you can let us know in the comments where you are listening from, and what time it is for you. Maybe it is late, and your room is dim. Maybe morning light rests on the edge of your window. It is a small human ritual to say where and when we are, and it reminds us that each person who listens is a traveler in time already, moving gently forward at 1 second per second. Time travel. Even the words feel like a trick. They carry the scent of paradox, of looping paths, of a clock that murmurs yes and no at once. Yet underneath all that, there is a scientific story that is unhurried and precise. It does not flinch from mystery, but it does not pretend. Physics tells us that time is part of the geometry of the universe. It can stretch and compress. It can flow differently for different observers. It can be navigated, at least a little, by speed and gravity. These are not opinions. They are measured facts, woven into the way satellites guide airplanes and phones guide sleepy drivers home. Before we go further, feel your own timing system at work. The pulse in your wrist, the rise and fall of breath. The way your mind drifts, returns, and drifts again. The body keeps time in cells and chemicals, in tiny oscillations of proteins and ions. The world keeps time in skies and shadows, in tides and seasons. We inherit clocks from trees and stars long before we build them out of quartz or atoms. In that sense, we have always traveled through time, carried along by rhythms older than language. Stories about time travel often begin with a bang, levers, and sparks. Ours will begin with a window. Outside, light from the stars is on its way to us. It takes time to cross the gulf. What you see is not a star as it is now, but as it was when the light began its journey. In the quiet of night, your eyes become instruments that read the past straight off the sky. This is a simple and honest kind of time travel, nothing like the shuffle of people through doors. Yet it is a real encounter with another time. Maybe we are already closer to the subject than it seems. As we move through this story, we will hold two ideas at once. First, time travel to the future is not just possible, it happens. Speed and gravity can carry a person into a different slice of tomorrow than they would have reached at rest. Second, time travel to the past is tangled with deep questions, with paradoxes and principles that may be as strict as the bones of the universe. We will not shout answers. We will sit with them. It helps to start with the ways humans learn to touch time, to count it, to name it. Long before relativity, people built sundials that transformed shadows into hours, water clocks that turned steady drips into minutes. the ringing of bells that gathered towns into a shared rhythm. Our tools changed our sense of the flow. When clocks improved, life synchronized. Trains demanded timetables, and timetables demanded agreement about what time it was, not just in one village, but across a continent. This practical pressure quietly set the stage for a revolution in how we understand time itself. Even now, we carry clocks everywhere, in pockets and on wrists, in phones and buildings and satellites. We expect them to match, down to the second. Yet the universe does not owe us that harmony. It is a gift we coax out of careful engineering, and underneath it, different observers still carry their own private time. This is not philosophy alone. It is measurable. Tiny but real differences accumulate between clocks that move and clocks that rest, clocks near the surface of Earth and clocks on mountaintops, clocks deep underground and clocks above the clouds. In the language of physics, every path through spacetime has its own proper time, its own stitch count along the fabric. There is a rootedness that comes from knowing that time is local and personal, not entirely a single shared river. It is like walking through a forest with friends. You all move forward, yes, but each path winds its own way between trees and shafts of light. Sometimes those paths converge, and sometimes they separate. The wonder is that we can compare notes afterward. We can gather in the clearing and see that one person took a longer way around and another found a shortcut. With time, the comparisons take the shape of experiments. They become evidence. All of this brings us to the threshold of modern physics. If time can flow at different rates for different observers, what does that say about the possibility of traveling not just into the future, but perhaps into the past? What does it say about the stories we tell ourselves about the arrow of time, about causes and effects, about memory and anticipation? Physics has a way of emptying our pockets of certainty, then handing back a quieter, deeper kind of trust. The questions become more subtle, more alive. We will take our time here. We will move from the first mechanical clocks to the insight that time and space belong to a single structure. We will look at the way light, with its constant speed, forces us to rethink simultaneity. We will sit with twin astronauts and see how one ages less while traveling fast. We will stand near a massive object and notice how gravity pulls not just on matter, but on time. Then we will peer into the mathematical corners where loops appear, closed paths that might link an event to its own cause. We will read the signpost there and try to understand whether the universe allows such loops or whether it protects itself from them. If you are listening while lying down, perhaps you feel a soft weight in your limbs, a gravity that keeps you close to the ground. That same gravity slows time a little here at the surface of Earth, compared to farther from our planet. It is a faint effect, measured with instruments that could sit quietly on your bedside table, but the principle is sweeping. If gravity can adjust time, then a strong enough gravity could change it radically. Black holes enter the picture. So do wormholes, those imagined tunnels through space-time that connect two distant places, and perhaps two different times. The words sound like science fiction, but the equations that whisper them into being are the very equations that predict the bending of starlight and the expansion of the universe. There is comfort in knowing that we can hold the wild and the careful in the same hand. We can let our imaginations drift over the landscape of possible worlds, while our feet stay planted on evidence. Even when the science is speculative, it carries a tone that is almost ethical. It asks for attention. It asks for kindness toward complexity. In that spirit, we will take a slow, steady path into the early ways thinkers understood time. How those ideas shaped instruments and calendars and lives, and how new ideas emerged when light itself told us something we did not expect. Let your breath settle. Let the ordinary sounds around you become part of the room. In a moment, we will step back in history to water clocks and polished brass, to philosophers who wondered whether time flows like a river or whether all moments exist at once. We will begin with the way people learned to count the hours and end with the insight that there is no universal now. That is where the possibility of time travel begins to turn from fantasy into physics. Let us begin. Time, before it is measured, is simply the way things change. Day opens, day closes. The moon grows round, then thins again. Warm returns to cold, and cold returns to warm. The earliest human timekeepers were bodies and skies. A person could look at the length of a shadow and feel the day's arc inside their own chest. Long before equations, there was this kind of knowing. It is still with us, even if it hides behind numbers. People learned to give that knowing a shape. A stick in the ground became a sundial, turning light into fractions. A bowl with a hole became a water clock, turning flow into count. In China and in Egypt, in Greece and in Mesopotamia, water clocks trickled in dark rooms. Later came sand, hourglasses pinching time into a throat of glass. The materials changed, but the impulse remained the same, to take the raw drift of experience and peg it to something steady. Every timekeeping device is also a theory of time. A sundial invites you to believe that time is tied to the sun. A water clock suggests a steady flow. A pendulum, introduced to timekeeping in the 1600s, invites you to think of time as a rhythm that can be tuned. When Galileo watched a chandelier swing in a cathedral and noticed that the period of a pendulum depends mostly on its length, not on the size of its swing, he glimpsed a reliable heartbeat in the world. That heartbeat became the basis of more accurate clocks, refined by Christian Huygens, and in turn, those clocks made navigation across oceans possible. Timekeeping and travel are braided together in our history. The sea taught us to tell time better, and better clocks made the sea smaller. With accuracy came synchronization. Cities began to share time. Trains demanded regularity across long distances, and train schedules dragged local noon into national noon. In the 19th century, time zones were introduced not by philosophers, but by station masters. It was a practical revolution that spread through telegraphs and timetables. Beneath it lay an assumption that seemed so obvious it was almost invisible, that there is such a thing as a universal now, at least within a time zone, and that the job of a clock is to stay aligned with that now. Newton gave this assumption a mathematical backbone. In his Principia, he wrote of absolute time, a uniform flow that exists independently of things. In his picture, time and space are a stage on which physics plays out. They do not participate. They simply are. That view brought enormous clarity. It allowed new predictions and new machines, and for many problems, it works extremely well. We still use Newtonian time for most of our daily lives. When you set an alarm, you are betting on a near uniformity that functions beautifully within the domain of slow speeds and weak gravity. Others challenged the absoluteness even then. Leibniz argued that time is a relation between events, not a separate entity. He saw time as a way of ordering changes, not a box in which changes occur. The arguments between Newton and Leibniz were dense, colored by philosophy and by pride, and they stained the margins of calculus with questions that would not resolve for centuries. What matters for us is that people sensed, even then, that time might not be a single, universal river. It might be more like a map drawn over the pattern of events, a map that could make one place look closer than another, depending on how you travel. As instruments improved, the picture grew more intricate. The 19th century uncovered something electric in nature, and something magnetic, and then something remarkable about the way light behaves. James Clerk Maxwell wrote down equations that described electric and magnetic fields as a single entity, and in those equations, a constant appeared, the speed of light. No matter the motion of the source, the equation said, light in empty space moves at the same speed. This was not just mathematics, it was an invitation to reimagine motion itself. How could a speed be constant for all observers, if in ordinary life speeds add and subtract? People tried to keep the old stage while making the new play fit. They imagined a medium called the ether, something that carried light waves the way air carries sound waves. The Earth was thought to move through this ether, and so scientists attempted to measure the difference in the speed of light in different directions. The Michelson-Morley experiment was a masterpiece of patience and precision. It found, within its sensitivity, no difference at all. Light speed seemed stubbornly the same. The ether began to thin in the imagination. Amid these puzzles, a young patent clerk in Bern kept thinking. He pictured trains and lightning, clocks and flashes. He asked simple questions with careful precision. If the speed of light is the same for everyone, what must we give up? The answer would become special relativity, but before we reach it, it is worth lingering on the humility of the approach. Einstein stepped away from heavy machinery and looked at basic principles, the kind you can carry in your head. He kept the equations of Maxwell. He kept the fact that the laws of physics are the same in all inertial frames, that is, for observers not accelerating. Then he accepted, fully and without hedging, that the speed of light in a vacuum is the same in all such frames. The consequences, even in thought, were radical. But even before Einstein, small hints of relativity existed in our daily practices. Consider the challenge of synchronizing clocks in different places. If you have two clocks in two towns, how do you ensure that they show the same time? You might send a signal from one clock to the other and adjust, but the signal takes time to travel. You must know how long it takes, and that depends on the speed of light. What if you are moving relative to the person sending the signal? The coordination becomes slippery. It is not just that synchronization is difficult. It is that the very idea of a shared now begins to fray when signals have finite speed. People already knew that signals take time. A ship at sea might see a lighthouse blink and receive the blink a fraction of a second after it happened. Telegraph lines crackled messages across countries, not instantly, but with delays that were tiny and sometimes noticeable. We learned to live with lag. Yet we had not fully absorbed what a universal speed limit means for reality. That deep understanding would open the door to time travel, of a kind that is not violent, not noisy, but steady and sure. Let us stand, then, in the soft hallway between centuries. On one side, Newtonian time is a trusted companion. Clocks tick in solidarity. On the other, light refuses to obey our habits. To cross this hallway, we will trade a single global time for something subtler. We will enter a world where time stretches and contracts, where simultaneity depends on who is moving and how, where the geometry of the universe itself binds space and time into a single fabric. In that fabric, paths can be long or short, not just in distance, but in duration. And to take a certain path is, in a precise sense, to travel into the future. We will walk into that story now with care. Bring with you the feel of a pendulum, steady and faithful, and the knowledge that it was only ever an approximation. Bring with you the train timetable and the telegraph's patient tap. Bring with you the idea that even practical problems sometimes demand a philosophical leap. On the far side of that leap, we will find that time travel is not the blink of a machine, but the natural consequence of moving through space-time itself. Then we will ask softly whether space-time allows loops, whether a path can fold back on itself, and if so, what the universe does to keep its story coherent. Imagine two bolts of lightning strike the ends of a long train as it passes a platform. A person standing on the platform sees both flashes at the same time. A person riding in the middle car of the train moves toward one flash and away from the other. The one ahead meets them first. The one behind arrives later. Both are right. Simultaneity has become relative. This simple thought exercise, carefully considered, carries us into the heart of special relativity. Time is not a single universal backdrop anymore. It is woven with space into one fabric, and that fabric adjusts to keep the speed of light the same for all observers. In this new geometry, time can dilate. A moving clock runs slow compared to a clock at rest, as seen by the person at rest. The faster the motion, the greater the effect. This is not an illusion. It is physical. If you carry an atomic clock on a fast airplane and compare it with the twin of that clock left on the ground, the times will differ by a measurable amount after you land. This is the Halfel-Keating experiment of the 1970s. It was not as precise as the experiments we can do today, but it was enough to reveal the reality. Later measurements with ultra-precise clocks flown on jets or left at different altitudes sharpened the picture. Muons, subatomic particles born high in the atmosphere, decay more slowly when they move at near light speed, living long enough to reach detectors at the surface. In their own time, they live the same brief span as always. To us, they appear stretched. Time itself along their path has traveled differently. There is also gravitational time dilation, a prediction of general relativity, which views gravity not as a force acting through space, but as the curvature of space-time itself. Mass and energy tell space-time how to curve. Curvature tells matter how to move. In a curved space-time, clocks do not all agree. A clock deeper in a gravitational well, closer to a massive object, ticks more slowly than a clock farther away. On Earth, this means a clock on the floor runs a tiny bit slower than a clock on a shelf. A clock in a valley runs slower than a clock on a mountain. The effect is small, but it is not optional. Even the GPS system depends on correcting for both special and general relativistic time dilation. Each satellite carries an atomic clock that, because of its altitude and its speed, would drift out of sync with ground clocks by microseconds per day if we did not adjust. Those microseconds matter. Without relativity, your phone would quickly lose its way by kilometers. Special relativity and general relativity were not just new theories. They were new ways of listening to the universe. With them, time travel to the future becomes as straightforward as a journey with a different route. If you live on Earth while your twin flies away at high speed and returns, the traveling twin will have aged less. This twin paradox is not really a paradox once you know that the traveling twin changes direction, which means they are not always in an inertial frame. General relativity steps in to account for the accelerations. The point that matters here is that you can, in principle, choose your path through spacetime to land in a future that is different from the one you would have reached had you stayed still. It might take enormous energy to achieve the necessary speeds, but the principle is thin air and clear sky. The past is more challenging. Before we walk into that challenge, it is worth pausing with a few experiments that anchor this in the ground. The Pound-Grebka experiment in 1960 measured the gravitational redshift of gamma rays moving in Earth's gravity. Photons climbing out of a gravitational well lose energy, and that loss shows up as a shift in frequency. It is another way of saying time runs differently at different heights. The Shapiro time delay measured how signals passing near the sun take a tiny bit longer to travel because space-time is curved there. We have watched clocks run slow near massive objects like white dwarfs and neutron stars by measuring the frequency of light they emit. We have seen the bending of starlight by gravity during eclipses, a sign that pathways through space-time are not straight. We have even imaged the environment around a black hole. Each of these builds trust, not just in equations, but in the idea that time is plastic in a particular way. Now, the question pulls us toward a deeper edge. If time can stretch and loop in the presence of gravity, could it loop so fully that you could travel into your own past? In the language of general relativity, this would mean there exist closed time-like curves, paths through space-time that return to the same event. Solutions to the equations that contain such loops do exist. Kurt Gödel found a cosmological solution that rotates where closed time-like curves appear. The solution is mathematically allowed, but it does not match our universe. Frank Tipler considered an infinitely long rotating cylinder. If you race around it in the right way, you might circle into your past. Our universe does not contain infinite cylinders. The interior of a rotating black hole, described by the Kerr solution, contains regions where the geometry becomes very strange, with the hint of paths that loop in time. But those interiors are cut by singularities and instabilities that likely forbid safe passage. In short, the equations leave a door ajar in some imagined rooms, but those rooms may be empty or unsafe in our world. Another idea that captures attention is the wormhole, a tunnel in space-time connecting two distant regions. Morris and Thorne, and later others, studied such objects with the serious playfulness of good physics. If you could hold a wormhole open, and if you moved one mouth relative to the other at high speed, or placed it in a different gravitational potential, the two mouths would become time-shifted. Step through one, and you would step out at the other at a different time, perhaps even into the past relative to where you began. The catch is that the kind of wormhole you could traverse seems to require exotic matter, material with negative energy density, to counteract the tendency of gravity to pinch the throat closed. Quantum field theory allows negative energy in small, fleeting ways, as in the Casimir effect, but quantum inequalities limit how much and for how long. The physics here becomes delicate. It asks not only what is possible in principle, but also what is stable and what respects quantum laws. Stephen Hawking proposed a chronology protection conjecture. He suggested that the laws of physics conspire to prevent the formation of closed time-like curves in any region where the classical picture would otherwise allow them. The intuition is that quantum effects ramp up near the edge of time loops, producing energy densities that destroy the would-be time machine. It is a conjecture, not a theorem. It captures a mood in physics, a suspicion that the universe forbids paradox at the level of causes and effects. Novikov's self-consistency principle also speaks here. It says that the only solutions to physical laws that can occur locally in the real world are those that are globally self-consistent. In a space-time with a loop, all events must fit together without contradiction. You can try to stop your grandfather from meeting your grandmother, but you will fail, perhaps in trivial ways, perhaps in ways that change the local texture while preserving the global shape. Quantum mechanics adds a whisper of strangeness. David Deutsch formulated a model of quantum closed time-like curves in which systems that interact with their past selves must satisfy a consistency condition. In this model, paradoxes are avoided, but at a cost to clarity. The universe finds fixed points, distributions of outcomes that fit past and future together. Seth Lloyd and collaborators proposed a different model using post-selection, where only outcomes consistent with a loop are allowed. These ideas are theoretical explorations, not engineering plans, but they show how the quantum world might handle loops without contradiction. There is also the suggestion, in one interpretation of quantum theory, that what looks like a paradox in one world looks like two consistent histories in many worlds. A choice that prevents your own existence might simply place you in a different branch where you are never born. If this feels like stepping into fog, it is not a failure. It is the truth of where we are. Time travel to the future is routine in physics. Time travel to the past is caught between the unusual geometry allowed by general relativity and the constraints that quantum mechanics is likely to impose. The best we can do is move carefully between possibilities and protections, respecting both. As we do, another thread becomes important, the arrow of time. Why does time seem to flow in one direction, from past to future? Why do we remember yesterday and not tomorrow? Within the equally valid equations of physics, time is symmetric at small scales. What then gives rise to the one-way feeling of now? The fact that eggs break and do not unbreak, that perfume spreads in a room but does not spontaneously gather back in its bottle. To understand the possibility of time travel, we need to listen to this arrow as well. Let us step into that quiet question next. We will bring with us the image of curved spacetime and the idea that loops are at least mathematically imaginable. We will place beside them the simple act of pouring cream into coffee and watching it swirl. We will ask what makes a mess easier to create than to undo, and whether that one-way street is as deep as bones or as soft as weather. In that blend of metaphor and measure, something about our place in time reveals itself. Consider a book that falls off a shelf and scatters loose papers across a floor. If you run the film backward in your mind, the pieces gather themselves, lift as one, and land as a tidy stack on the shelf. The underlying laws of motion, if you look only at the small parts, do not forbid that. Yet you will never see it. The difference between forward and backward here is not in the equations for particles, but in the conditions under which they move. The second law of thermodynamics tells us that entropy tends to increase, that systems of many parts, left to themselves, wander from order into disorder. It is a statement of probability, of how extraordinarily special certain arrangements are. The arrow of time, in this view, comes from our universe beginning in a state of low entropy. From that improbable starting point, it has been unwinding into richness ever since. Entropy is a slippery word made gentler by images. Picture a perfume bottle in a quiet room. You remove the stopper. Molecules rush out and spread until the scent is everywhere. To reverse that process would require a conspiracy of mind-boggling precision. You would need each molecule to find its way back. The rules would allow it, in theory. The odds are so low that for all practical purposes, it never happens. That practical purpose is our world. We cook and rearrange, we age and remember, because we ride the gradient from order to disorder, from special to typical. It feels like a flow. In the mathematics, it is a drift. This arrow of time shapes all stories about time travel. It tells us why we can travel into the future by sleeping or by flying fast, yet still only wake in a world where coffee cools, where new memories form, but old ones stay fixed. If you were to return to a past moment, even if the geometry were kind, the entropy accounting would be merciless. To land in an earlier state of a macroscopic system without rewriting a staggering number of microscopic coordinates would be to attempt something near impossible. It is one reason why even visions of time travel that rely on self-consistent loops feel so otherworldly. They require a choreography of atomic detail beyond practicality. The universe, left to its own patterns, does not rewind. There are other arrows. The cosmological arrow points from a dense, hot early universe to a sparse, cool later one. The radiative arrow points from sources to receivers, from causes to effects in the way waves spread. The psychological arrow points from past to future in our minds, from memory to anticipation. These arrows align, likely because they emerge from the same condition, a remarkably smooth beginning. This does not mean the future is predetermined in a way that crushes choice. It means that the boundary conditions of the universe are such that many paths open forward, while few return. Freedom lives inside the flow, not outside it. Even within this flow, relativity allows time to be local and personal. Clocks tick at different rates along different paths. This gives us a language for time travel that is honest and grounded. Ride a fast spacecraft, and you will return with a shorter personal timeline than those who stayed. Live at high altitude, and you age a tiny bit faster than someone at sea level, as measured by ideal clocks. Spend time near a massive body, and your time slows. We build these offsets into our technology. Every time a phone finds its location, tiny adjustments for relativity guide the answer. Every airplane route that listens to satellites is using a cascade of corrections that blend speed and gravity. Without them, the world would be lost by meters and then kilometers. The future is already different for each of us in small amounts. It is not a fiction. It is an everyday truth. What, then, of loops and paradoxes? Physicists have rehearsed them with careful imagination. One famous thought experiment, suggested to Kip Thorne by a student named Joseph Polchinski, involved a billiard ball entering a wormhole and emerging in the past at just the right angle to strike its earlier self, preventing it from entering in the first place. That is a paradox. The resolution in a self-consistency view is that the ball emerges at a slightly different angle, nudges its younger self just enough that it still enters the wormhole later on, making the loop consistent. No contradiction, but also no freedom to create one. The loop edits its own details to survive. In other approaches, the loop branches reality, and in the branch where the ball is struck, there is simply no loop. The paradox dissolves into multiplication. We can hold these as shapes of thought rather than commitments. They help us see that even if closed time-like curves exist in some extreme corner of space-time, they are tightly constrained. They are not merry-go-rounds for changing history. They are networks of consistency that permit only those cycles that fit, or else they are invitations to branches where a single history never contains a contradiction. These are not everyday options. They sit near extremes of gravity and quantum theory, far from any laboratory we can build. Stephen Hawking's intuition that physics protects chronology may well be right. Quantum fields may turn any would-be time machine into a fountain of energy that destroys itself. If that is so, it is a kind of kindness, a way the universe keeps its narratives from fraying. There are speculative ideas that offer a softer picture of time. Some researchers have explored the thought that time might be emergent, a property that arises from entanglement and correlations, rather than something fundamental. In certain approaches, like the Page-Wouters mechanism, time appears to be what you get when you compare part of the universe to a clock subsystem, with the whole in a timeless state. There are studies of indefinite causal order in quantum processes, where events do not have a fixed before and after until they are embedded in a larger experiment. These do not give us time machines. They give us humility. They remind us that the way we slice the world into moments is not the only way the world can be. We can return to analogy, which often carries truth better than heavy words. Picture a river. Most of the water moves forward. Here and there, eddies form behind rocks. In those eddies, a leaf can circle, drifting backward relative to the bank for a short time before rejoining the flow. Closed time-like curves, if they exist, would be like such eddies. They would not reverse the river. They would be local features in a larger current that never stops heading downstream. Entropy is the grade of the riverbed, the slope that draws the water on. It does not forbid small swirls. It does make it nearly impossible for the whole river to climb the hill. Another image. Think of time as a quilt. Each square is a local patch, hand-stitched to its neighbors. A pattern is coherent at distance because of the stitching. A closed loop would be a part of the pattern that curls around to meet itself. You could follow the stitching if it is there, but you cannot force the cloth to join where there is no seam. The universe is likely quilted to prevent such forced joins. It allows what the pattern supports and refuses what would tear the fabric. In our daily lives, these grand structures reduce to something simple. You are a time traveler already. You carry your own clock. Your path through the world is shaped by your choices, by gravity and speed, by the company you keep and the rings of Saturn that you will never see up close. You move from morning to evening and find new things along the way. The physical possibility of leaping far ahead by speed or gravity is a wider version of that same truth. The physical impossibility or near impossibility of returning to change the past is a comfort. It gives the past a kind of dignity. It lets us work with what has been, not against it. Let us carry that comfort into the final part of our journey. We will connect the science to the way we live, to the way we remember, to the way we look at the night sky and see messages sent long ago. We will ask what it means to be brief and steady in a universe where time is both firm and flexible. We will listen for gratitude in the physics and find that it is there, quiet, waiting. There is a moment many people share, whether in a city or in the country. You step outside at night and look up. Even through haze, you can often find a bright point or two. On a clear evening, you may see a river of stars, a pale wash across the sky. What you are seeing is a museum with no walls. Each point is a piece of time, preserved in light. Some are years old. Some are thousands of years old. Some are millions. The Andromeda Galaxy appears as a soft smudge to our eyes, and the light we see began its journey when humans were first learning to shape fire into tools for living. Every stargazer is a curator of ancient signals. We time travel this way without moving our bodies. We also time travel with machines that move for us. Every probe we send to the planets carries a clock. The clocks run a little differently than our clocks here. When Voyager 1 looks back and sends us a pixelated whisper from the edge of the heliosphere, that whisper takes the better part of a day to arrive. By the time we receive it, the craft has already moved forward, and so have we. Yet we can reconstruct the past moment, place it on a timeline, and listen to it as if it were happening now. Time in space is a dance of delays that can be measured and cherished. Closer to home, the technology we rely on hums with relativity. If you are listening to this on a phone, there is a quiet chorus of corrections beneath the screen. Satellites high above you carry clocks that tick a bit faster because they are farther from Earth's gravity, and a bit slower because they are moving quickly. Engineers account for both effects so that the signals arrive in step. It is like guiding a choir where each singer hears the music at a slightly different time. You adjust, and the harmony appears. The result is that a map opens and a dot settles on a street where you actually are, not where you would have been if Newtonian time were the whole truth. This is everyday time travel, translated into practicality. If you ever fly long distances, you live a small twin story. You age a little less than those who stay on the ground. If you live high in the mountains, your time flows a touch faster than people at sea level. If you spend time in a deep mine, your clock ticks a hair slower. These differences are tiny. They will not reshape your life. But to know they exist is to feel the universe as a crafted thing. It is to sense that the rules are consistent and tender. You are not just in time, you are in your time, and the stitching that makes that possible is the same stitching that holds galaxies in their spinning. What about the past that we cannot visit? In stories, people go back to save, to change, to fix. In physics, the past is a landscape of records. Fossils are records, keeping the shape of bones and leaves from millions of years ago. Ice cores are records, holding breaths of ancient air. Tree rings are records, tracing good years and lean years across centuries. Your own memories are records. They are not always accurate. They drift and reform. Yet they are rooted in a one-way process. Biology writing with chemistry into the soft paper of a living brain. We tend those records. We share them. We take responsibility for them. In this sense, the arrow of time asks for care. If there is no way to change what has been, there is still a deep way to honor it, to understand it, to let it teach. There is also the future that we will reach, 1 second after the next. We like to imagine leaping across it with impossible machines. Physics suggests that the most honest leap is the simple one. Take a different path. Spend time under different gravity. Move gently faster or slower relative to the ground. These are not heroic acts. They are the ones we already perform in miniature. The romance is quieter than fiction, but it is no less beautiful. It asks us to find wonder in a steady movement, not just in an extraordinary jump. As for the radical possibilities, wormholes and loops in worlds that branch, we can hold them as forms of meditation. They may be barred from our universe by rules we do not yet fully know. They may exist only as mathematical landscapes we visit by thinking. There is value in walking those landscapes with care. They help us ask better questions about causality and consistency, about the relationship between big-scale geometry and small-scale quantum behavior. In the end, they may tell us less about building machines and more about the boundaries of understanding. That is still a gift. You, being alive now, are part of the reason the arrow of time feels the way it does. You remember the past because your brain is a structure that encodes history. You anticipate the future because your mind runs simulations, tiny models that test possible outcomes. A large part of being human is navigating that blend, taking in the world as it is, as it was, and as it might be. In a universe where time is both flexible and one way, that navigation is an art. It is also something like love. We care for what comes next because we cannot return to what came before. We make better futures because we can only arrive at them once. The science leaves us with a quiet conclusion. Time travel to the future is real. It is built into the structure of space-time, into the way speed and gravity shape our personal durations. Time travel to the past is not something our world seems willing to offer, at least not in a way that allows contradictions. Loops may be possible in extreme and hypothetical spaces, but they are not for the undoing of choices. The arrow of time rises from a rare beginning and carries us forward. It asks us to make peace with change and to find meaning in passage. There is something tender in this. It says that cosmic rules and human lives rhyme. Our limitations are not punishments. They are invitations to attend. When you watch the slow shadow of a tree move across your wall, you are watching the earth turn, the sun blaze, and the geometry of space-time perform a quiet, ancient dance. When you hold a photograph of a younger self, you are receiving a message sent from a past you cannot visit, but can still hear. When you listen to a song from years ago and feel something in your chest, that is a kind of time travel too, the kind that moves through memory rather than space. If you would like to make a small ritual out of this, you can write a note to your future self. Place it somewhere safe. Set a reminder, not in haste, but with patience. In a year, or in 5, the note will arrive on the only time machine we truly own, the one that carries us through nights and mornings. When you read it, you will have traveled. Not flashy, not loud, but real. Thank you for spending this quiet hour in the hypnosphere. If you found rest and wonder here, you are welcome to return. You can subscribe if you wish to keep this gentle stream close at hand. No hurry, no pressure. Simply a place to settle, breathe, and keep learning together.